So I'm Harrison, and I'm an ECE student, and this is topological insulators for magnetic memory. And to start with the motivation for why we want to use magnetic memory. So as we see that computing gets more and more complex, we see that the scale of data centers as well are increasing. And with this increase in scale, we can see that technologies such as SRAM use very large amounts of energy, even in idle operation. And this is just unideal in general. So we can now look towards non-volatile memories as these memory elements instead. And specifically within that, we are looking at spintronic devices. And these are nice because MGJs are back-end compatible with CMOS technology, as well as being high-speed, low-power switching devices. I forgot the references for those, but. So looking specifically at MPJs, this might just be a review, but there are two ferromagnetic layers separated by an insulating MgO layer. So on top, we have a pin layer, and these are usually made out of CoFeB, cobalt, iron, boron. And this pin layer on the top is pinned using a synthetic antiferromagnet. And we have a free layer on the bottom. And this free layer has a spin down, spin up region separated by a domain wall. And MPJs can be used to encode information using the difference in relative magnetization between our two ferromagnetic states. And in this example specifically, we have an SOT spin orbit torque magnetic tunnel junction. And I'll get into that next slide why that's important. But otherwise, when we're in our parallel state or a low resistance state, we have both of our ferromagnetic layers magnetized in the same direction. And that means that these, in this example, they will conduct spin-off electrons very easily. But when we enter our anti-parallel high resistance state, so we have our pin layer spin up and our free layer spin down, it will scatter electrons of both polarizations and lead to a high resistance. And the switching mechanism that I'll be exploring today is spin orbit torque. The other of which is spin transfer torque, which is an injection of current in plane into the ferromagnetic layer. But with spin orbit torque, current is passed through a heavy metal layer adjacent to the free ferromagnetic layer. And these heavy metals usually have a strong spin orbit coupling and use a property called spin Hall effect, in which a spin current is transverse spin current is generated in perpendicular to the direction of applied electric field. And in general, spin orbit torque converts charge currents into spin currents. And we can quantify this efficiency using the spin Hall angle, which is just the ratio of spin current to charge current. And overall, this is a fast, efficient, and high endurance way of switching MPJs. Oh, and the common heavy metals currently used in MPJs are platinum, tungsten, and tantalum. So the kind of spin Hall angles that we can see in those devices, for example, with beta phase tungsten is around -0.3, and in platinum it's around 0.1. But now we can look at topological materials. So topological insulators are a unique class of materials that are topologically protected. And they're unique because they have a bulk energy gap that is defined by, that is separated by the highest occupied electron band and the lowest empty band, similar to what you would expect in an insulator. But their surface and edge states are gapless. So at their surface, they behave like conductors, but in their bulk states, they are insulators. And and there has been, although these types of materials are relatively new, there has been some work done on them recently. And here is a BISB2 to E3 growth, and shown right here. And so this was done using both molecular beam epitaxy in combination with sputter growth, as well as a pure sputter growth. And with that, we have the molecular beam epitaxy growth resulted in a 102% TMR with a critical switching current of 1.8 e to the 5. whereas the sputter growth had a slightly worse TMR around 90%. And its critical switching current was also around an order of magnitude greater. And lastly, using spin orbit torque ferromagnetic resonance, the spin Hall angles of the in-plane sample were measured at 1.59, and the perpendicular magnetic anisotropy sample is measured at 2.5. Oh, and then furthermore, these are both measured from the in-plane sample. So on the right is the hysteresis loop, the field loop, and then on the right we have the resistance and TMR measurements. So what are some of the challenges surrounding topological insulators? So topological insulators have very large resistivities, as is the nature with the materials that have strong spin orbit coupling. And we can see this in the spin Hall angle, where the proportion of spin current to charge current leaves a very small charge current, which does naturally means that it's less conductive. And a common problem with all magnetic tunnel junction devices in general right now is that they have low TMR ratio, which is its on-off ratio. So the most competitive devices right now are upwards of 200 plus, some being as high as 600. But as shown previously with our topological insulator, MTJ, it was only 100%. Although DFT calculations have predicted higher possible values. And also the complexity of fabrication and integration for topological insulators specifically, because a lot of these materials have complex crystalline structures, the reliance on MBE growth right now poses a lot of problems with integration at a more industrial level. Yeah.